Okay, guys, I'm going to talk a little bit about conservation of angular momentum with this Planck problem. Um, so there's two main components here we're going to have to do. We're going to have to first figure out conservation momentum of angular momentum to figure out the rotation rate with which the Planck swings upwards when the ball hits it. Then we're going to have to figure out conservation of energy to figure out the change in height of the center of mass of the plank or of the wooden board, right? How high does the plank swing? It's going to be the height of the center of mass, okay? So that's something you probably don't know, but that's what we do here, okay? When we figure out this problem, figure out how high does the center of mass swing. We can figure out the angle from that, but the only way to do conservation of energy is to track the center of mass change in height. That'll give you the change in gravitational energy of something even that's rotating. It's kind of interesting. A disk rotating wouldn't have a change in gravitational energy, but a plank rotating obviously would have it. If it was somebody on a swing, like a pendulum, right? We would track the change in height of the mass. Well, that's because that's where the center of mass is. So a plank swinging, we track the change in height of the center of mass. It's the delta H. So we'll see that in a second. Let's first figure out the speed with which this thing rotates up at. So the trick here is to treat the ball, incoming ball, as if it has angular momentum the instant right before it hits the plank, because, well, this is basically a 90-degree angle, the angle between the radius and the velocity, basically 90 degrees, approximately 90 degrees, right? So we can say the ball has angular momentum. In fact, you can say anything moving, because this is the rotational axis, you can say anything moving in a straight line has angular momentum. As long, because it has a radius. That radius is changing as it moves relative to the x. But you can always say something moving in a straight line has angular momentum, but it's always relative to some point, relative to a point. So the angular momentum of the ball gets transferred into the angular momentum of the wood. All right, so the angular momentum of the ball is mvr sine theta. The angular momentum of the wood is the moment of inertia of the wood times its angular velocity it swings up with. All right, and that's what we're going to find. We're going to find the angular velocity. It says how fast does the plank swing? Well, remember, when you're dealing with an object, how fast? Well, that depends on how far away from the axis you are, right? If you put a speedometer on the outside edge of this, as it spun up, this would move an arc length that long while it turned through this angle. Here, it only has to move an arc length that far while turning the angle. As you get closer to the center of the circle, the arc length goes down and gets smaller, so therefore you're covering less ground in the same amount of time it takes to swing up. So in fact, the outside edge of this would have a measure, if you put a speedometer on it, would measure a greater speed than the middle. The middle would measure a greater speed than a point right towards the center. So omega for all points on this is the same, the omega, because it's got to turn the same angle in the same amount of time. Omega's angular velocity, delta theta over t. So anyway, we'll figure that out, and then we'll figure out the speed. Will it make it all the way around? Big hint. No, it won't. And how would you figure that out? Well, it depends on a couple things. We'll see that in a second. So first of all, let's figure out omega. What's I? I of a plank. Well, it turns out that for this, I probably should have given it to you, but it's kind of like the rod about one end. It's 1/3 ml squared, where L is the, I'll make it a lowercase l to not confuse it here, where L is the length of the board, all right, which also happens to be R here, right, this R. It's the length of the board. So let's go through and plug some stuff in here. So this is the mass of the ball, velocity of the ball, radius the ball hits from the rotational axis, which is going to end up being the same as L. So we're going to put an L for that. So it's MBVBL sine theta. Well, it's approximately 90 degrees, so that's just 1. Then we have 1/3 mass of the wood times the length of the wood squared times omega of the wood after the collision. So the angular momentum of the ball goes into the angular momentum of the wood. One of these L's cancels. You end up with omega of the wood is equal to 3 mass of the ball times velocity of the ball divided by mass of the wood times length of the wood. You plug everything in. The omega, the angular velocity, ends up being 15, I think. Check my calculator. 15 radians per second, I believe. All right. So that's the angular velocity with which this wood initially starts to swing up. So omega equals 15 radians per second. All right, and let's just treat that as the speed, I guess, or I don't know. We'll have to figure out in a couple spots. Okay, so there we go. That's part A. The speed of the outside edge, to get that, V of the outside edge would be just R times omega, so it's 0.5 times 15. It would be 7.5 meters per second. So out here, we're moving at 7.5 meters per second. Let's go ahead and figure out the center of mass speed. Velocity to center mass would be 0.25, because that's the distance, that's the radius of the center, times 15, which ends up being 3.8 meters per second. So the center of it is moving at 3.8 meters per second when the ball initially collides with the plank. The outside edge is moving at 7.5. The inside edge, right at the axis, is moving at 0. So now let's figure out how we apply conservation of energy to this. All right, so the center of mass velocity here is 3.8 meters per second. Now, you would never be able to figure this problem out on your own unless you've seen it before. Okay, you have to see this problem once to be able to do it. Now, so we can ignore the ball. The ball stopped. It's no longer part of the problem. All right, this plank is going to swing up. So it's all kinetic energy here. The velocity now, we treat it, you can do I omega. You can do I omega. We didn't really have to figure out the VCM. We could do I omega. That's fine. It's all rotational energy here. And then once it rotates up to this point, it stops rotating, and it's all gravitational potential energy there. So the initial K rotational equals the gravitational potential energy at the top. Now, how the heck do you figure out the change in gravitational energy? Well, it turns out delta UG of this is equal to delta UG of the center of mass. It would be the same thing for a regular pendulum, right? When a regular pendulum swings up, we did conservation energy of the object. Well, that's because the center of mass of the pendulum is the center of mass of the mass, right? That's hanging. So the change in height of the mass is always referenced by the change in height of the center of mass. It's the same thing for something swinging up like this. It's the change in height of the center of mass that gives us the gravitational potential energy. So how high does it swing? That means how high does the center of mass change. So I gotta quick finish up this video, a couple minutes. My wife's got a meeting, but anyhow, 1/2 I omega squared. I omega squared goes into mgh. It's 1/2 of 1/3 ml squared times omega squared equals mgh. We get a little bit of cancellation here. I'm going to free myself up some space over here. We get an m canceling, right? So we get 1/6 of L squared omega squared equals GH, or the height it swings up to is L squared omega squared over 6G. I can plug some stuff in here. The length of this board is 0.5. I'm not going to put units on here. 15 divided by 6 times about 10, right? All right, so you plug it all into your calculator. You get a height of, oh shoot, I lost it here. I think it's like 0.93 meters, which is, wait a minute, how could it do that? Well, it can't. Turns out it would spin all the way around. So the total change in height here could be 0.5 at most, right? So that means, in fact, when it gets to this, it would have a maximum amount of potential energy, but it would still have some kinetic left over, so it would swing all the way around. So I lied earlier when I said it doesn't make it all around. It makes it all around. It doesn't make it all around, in fact. Kind of surprising result, but the whole thing is this ball stopping, right? It transferred all of its momentum. You know, that momentum is fairly big. But yeah, there you go. Now, to finish this problem, assuming the ball sticks, you pretty much have to go back to the beginning now and do this problem again. So this is what I want you to do, right? You still have to do L before equals L after, right? So the ball coming in equals L after. So the ball coming in has all the initial mvr sine theta. So the mass of the ball, velocity of the ball, r is still hitting the outside edge, so I'm going to put an L there. L after is, now it's there's two things rotating, right? The ball sticks. Initially, it still has mass of the ball, velocity of the ball times L. This is after the collision of the ball, plus I omega. Now, the trick here is, if the ball is stuck to the plank at the outside edge, right, and they're rotating together, the velocity of the ball is R omega. It rotates upwards at the same rate as the plank. All right, so we're looking for omega here, right? Because then we're going to use that in our kinetic energy formula. So velocity of the ball equals R omega. So we put that in for the velocity of the ball. So mass of the ball, velocity of the ball before the collision times L sine theta is just 1. All right, mass of the ball here times R omega. R is L. Omega is omega. Times L again. Plus I omega, which is 1/3 mass of the wood. L squared times omega. All right, so look, these two would add up because look, they're a mass times omega times L squared. You can cancel out an L from both sides. All right, and then go from there. Remember, this is the velocity of the ball before the collision. So now the momentum's divvied up between the two rotating up together. This is the mass stuck to the end. So mass of the ball, velocity of the ball. It's kind of like when you do conservation of energy, where one of the radius cancels out and it ends up looking just like a normal conservation of energy equation. So you get mass of the ball times L omega plus 1/3 mass of the wood times L omega. And then solve for omega. So you got to add these together, solve for omega. You get omega, and then you say K rho equals mgh. But now, all right, you have two things changing height here, which that gets a little more tricky as well, right? You got to do mg delta h of the ball, all right, plus mg delta h of the plank. And for the ball, it's going to be different, right? the change in height of the ball is going to be different than the change in height of this. See if you can figure that out, how they relate to each other. I'll be writing up a solution. This is a hard question when they stick. It's much easier when the ball sticks at the center of mass. All right, much easier when the ball sticks at the center because then they both have the same change in height. It's geometry. See what you can do. That's a challenge question. You guys are AP Physics C students. See what you can do with that. All right, see you later.